I'm a PhD student at the Faculty of Physics here, and today's presentation aims to give you a glimpse into the answer to this probably provocative question. But this work isn't done just by myself, of course, and it's a collaboration between University of Warsaw and Institute of Photonic Sciences in Barcelona. And I'm working with Dr. Alexander Dauphin, Patrick Wembeli, under the guidance of Dr. Michał Toms and Professor Maciej Lewenstein. My main research interests lie in the field of quantum many-body systems. So these are basically systems composed of particles that can move, they can interact with each other, but to fully acknowledge all phenomena happening there, you need to take into account quantum mechanical description. This is basically what quantum many-body systems are. And the problem is they're very numerically demanding. So for the last few years, physicists started to use machine learning methods to deal with this problem. And especially abundant research was done in the phase classification field. And this is basically where we enter. We can really ask the machine about the state of the quantum mechanical system, and the machine can tell us whether it's in the phase 1 or phase 2, but we don't really gain any new knowledge. We get a box that does some task for us, but we don't really gain any new physical insight into what's going on. So this is where we enter, and we want to really extract the knowledge that the machine gains and maybe enrich our own. So this would be main motivation for what we're doing. And we will start from really brief introduction to phase transitions. I will do it in a slightly different way than in the previous talk, so I hope you won't be bored. And then I will discuss the topic of interpretability of machine learning and existing tools, with a special focus on influence functions that we use. And in the end, I will present you preliminary results that should give first a glimpse on this answer to this question. So we do encounter phase transitions since high school, or not high school, elementary school even. So we all saw the water can have different phases, as we saw also in the previous lecture. And so basically phases are different behaviors, different patterns that a system exhibits. And the changes between phases are driven by some parameter, here by temperature. And in the case of the water, it's pretty intuitive what's going on. But if we go to more abstract models, it's good to have more formal description of the system. So here goes the order parameter. So this is the quantity that is very different in one phase and in the other. And the transition point is visible when you look at the change of the order parameter. And here, if we would like to get more formal with the transition between ice and water, such an order parameter could be density of the system. And you can see that it abruptly changes in the zero temperature, what shows us that there is a transition. And immediately we can see that this is one first type of the transition I'd like to show you. Namely, if we have a jump, if we have a discontinuous change in the order parameter, the transition is first order. The definition of the order parameter depends on the system and the phases we want to analyze. And other example would be magnets that can be either disordered, so like some of these magnetic moments would be around 0, and versus the ordered phase, where the magnetization is non-zero. So this would be a different order parameter, and you can see that one can see that the system can be driven from one state, from one phase to another, with the temperature. So it's again the same external parameter that switches the phases. But this time, if you plot the order parameter being magnetization, you can see that the change is continuous, but the derivative is not. So the transition is second order. And so this was like really crash course on phase transitions. And what I want you to remember from it is we have different phases. They exhibit different behaviors. We can describe them with order parameter. And the way of the change that this order parameter exhibits describes us the type of the transition. And physicists are not only interested in what phases the system exhibits, also how the transition goes. So this would be actually, I think, everything you need to know for the physics part of the talk. Now I'd like to switch to the topic I think most of us were already concerned in the life about, and it's about interpretability of machine learning. Before moving to that, let's fix definitions so we all think about the same stuff. So first of all, we have black boxes that have some logic, but it's inaccessible to the user or it's hidden. And the most popular example of the black box in the machine learning would be some deep neural networks. We would love models to be interpretable for various reasons, but what's interpretable? It's an ability of the model to explain itself, to explain its decisions in understandable terms. And this last sentence is pretty interesting because you see that in both definitions there's a user. So we should wonder, when you're doing an interpretability tool, we need to wonder whether the user is a scientist or data scientist or maybe just regular guy, and how fast the decision-making process has to be. Maybe it has to be taken in milliseconds, or maybe you have like few days to analyze the interpretability tool results. So this was just like small aside, but I think it's very important to remember that there's this human factor inside, and it's pretty interesting. And these reasons I was mentioning, besides the physics that I will be talking about mainly, that we want to have the insight into the inner workings of the machine, because otherwise we don't really get any new insight on physics. There is a legal reason that because European Union May last year introduced the bill that gives right to any individual to get a meaningful insight into any automated decision-making process. And this is this is surprising in a sense that I think it's kind of underestimated area in machine learning. But, law says that we have to deliver, and I think that's one of the really good reasons why we should take it into account. But also, these tools can reveal biases that are inherited by machines from humans that label data. So this is also very interesting, very important also issue from everyday life. And there's physics, so the most important thing for me. And one of the tools that can deal with this issue is called influence functions, but there are many. I mean, like once every week an archive about new methods comes, but I mean, I feel they are produced in a very quick manner, and maybe it's like whole overview that is kind of lacking. But influence functions are very interesting tool because they have pretty intuitive meaning. So they basically tell you how important is the given training example for a given prediction of the machine. So they are analytical approximation of the leave one out training. So how would the prediction change if you had removed the given training example from the training set? And this is pretty exciting because doing it by hand would be like prohibitively expensive. It would, I mean, for a MNist to analyze one given prediction and all points and find the most influential one, it would be like 50,000 trainings. So this is very expensive. And the derivation is in this paper, and it's pretty straightforward, but it has few important assumptions. And let's look at the equation for a second. So this is to calculate the influence function, how influential a training point is for a given prediction. You need a test loss at a given you need a test loss, you need a training loss, and then you need a Hessian, and it's the inverse of the Hessian. So I think we can immediately see two problems with that. First of all, you have the inverse, so you cannot have 0 eigenvalues, because otherwise the inverse doesn't exist. And second of all, you need to calculate the Hessian, which is huge for complex models. Good news is that we don't need to really calculate the Hessian explicitly. We can approximate it, for example, stochastically, as the authors did, but we won't focus on that more. I mean, it's doable, and it just introduces small noise to the results, so it's not really a big problem. Kind of a big problem is the fact that this demand of the loss that is strictly convex, because well, definitely we can say many things about deep neural networks, but they are not convex. And I think that the most important delivery from this paper is that they showed that this tool, even though it demands the strict convexity, delivers significant results, even if we just quadratically approximate the minimum. Just by adding this damping term that basically adds up to the Hessian the value that is bigger than the biggest negative eigenvalue, so makes all eigenvalues positive. And still, in this case, it does deliver interesting results. So the authors of the paper showed that for the given prediction, they took one example of support vector machines, and they took an inception neural network, and they showed that the most influential examples for both are pretty different. So the inception shows that the most influential training examples are the ones having exactly the same type of fish, while with the support vector machines, it just shows some aquatic creatures. So they claim that this tool allows you to judge how well the model learned what you wanted it to learn. And we will use that to apply it to physics as well. So this brings us to our physics problem. And just to tell you the motivation again, because it's pretty crucial. So if we can show that the machine learns in the phase classification really the order parameter, it will be actually the first real proof that it does, because so far we just trusted the accuracy on the test set. And I mean, for sure it learns something correlated to the order parameter, but we don't know if it's really order parameter. If we show it something else, then, well, this is pretty, I think it's pretty unlikely, but still, maybe there's some accidental correlation that it learns, or maybe there's some background, or maybe there's some background information we give as a scientists. And the most exciting, of course, is maybe it does learn something meaningful, and it would be some kind of new physics. I mean, this is like dream-like result, of course, but well, one can, hope so. And we chose to play with a really simple physics model. It's like toy model. So we have a particle, we have a chain, we have like different sides. The particles can hop between the sides with some amplitude, and they interact with each other. They can repel each other with some interaction strength u. So you can imagine that from this interplay of the interaction, this repulsive interaction, and the hopping amplitude, we can get two phases. So first of all is this uniform mean occupancy. So there is no preferable site for any particle, and the distribution is uniform. And when the interaction term gets bigger, they want to repulse each other more and more. So the mean occupancy is modulated. And we can describe it in the terms of order parameter. So it would be difference of mean occupancy between two neighboring sites. So we get order parameter 0 for here and non-zero here. We can also plot that, and we can see that it's continuous, so it's second order transition, and that the transition gets somewhere here, so when interaction is around half of the hopping. But okay, just to remind you, this is simple model. We know everything about it. There's no new physics going on. Right now, we're checking whether the influence functions is a good tool and can tell us anything interesting. And before going to the results, because you will see a few pictures like this, let's discuss what all parts of this plot means, because this is the meat of the presentation. So we have on the y-axis, we have influence functions value. We have this ratio of interaction between the ratio of interaction in hopping. So this would be this. This is exactly the same x-axis as here, and we calculate this influence function for really small CNN trained on to classify these two phases in the system. And by small CNN, I mean like 800 parameters, so we can calculate Hessian exactly, so we don't have any noise. And this is the transition point that is marked. So this is this point when the order parameter starts growing. This is, and this is important because this will be switching, this is the test point. So this is the ratio for which the test point, the currently analyzed test point, is calculated. Finally, these all are training examples calculated for different ratio. The red ones are 5 most harmful ones, and the green one are the 5 most helpful ones. So basically, we will see how, when switching from the different test points, how this influence function pattern changes. And we'll try to say something about that. And before showing you, I will tell you what to expect. So if the machine learns order parameter, look, here it's exactly 0. So all states here, like regarding order parameter, are identical. So there should be no correlation between distance in this ratio and the influence function value. While here, if it learns the order parameter, it should be the most influential points, I mean, we imagine, should be the ones that are nearest in this, let's say, ratio function. But look what's going on. Okay, so this is the first plot. We look at the test point that's calculated at 0. So this is promising because, as you can see, the most influential, the most helpful ones are kind of evenly distributed around this 0 phase. So this is good. This is what we expected. However, when we switch to the transition regime, okay, when we switch to transition regime, it still makes sense exactly as we thought, because the most influential ones are in the most helpful ones are really close to the test point we are analyzing. Still good, worse, 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 and now it turns out that when we go far away into the phase 1, far away from the transition regime, still the most influential points are the one in the transition regime. So this was surprising, and somehow it may mean that the most important information is contained for the machine, is contained in the transition regime. Whether it disproves that it learns order parameter, we still need to understand that really well. But in this regime, it behaves exactly as we expected. So this is still work in progress, especially in the part that we need to understand what's going on. But for sure, we can see that we have 3 different behaviors depending on the place that the test point is. So this for sure tells us that it gives some meaningful results. So
What is the
test point? So this is like prediction. So we ask the machine in which phase is the point taken for this ratio. Okay. So. So conclusions would be that I think that influence functions will give more meaningful results. For sure, what we want to check is whether it's sensitive to the type of the transition, because if the behavior of the influence functions is completely different for the first type transition and second order transition, and preliminary results say it is, then we should expect that it's possible to use this tool to distinguish different types of the transitions that we never knew, but we train the machine to classify these phases, and then we can judge by how it's trained on the type of the transition. So this would be really, really cool. And thank you for your attention.